Hello and welcome to Toddcast number 23. I'm going to cover constitutional isomers. We alluded to that in a previous Toddcast, so we'll go through that one reasonably quickly. And then unsaturation, which we also have addressed a couple different ways. We talked about saturated fats versus unsaturated fats, and then also repeated again, we talked about aliphatic alkanes versus cyclic alkanes. And so these will be hopefully familiar topics, but it doesn't hurt to rehash them. So, with that in mind, let us start. So, constitutional isomers again have the exact same atoms because they're isomers, but they're connected differently. They're not bonded the same. So, for instance, if I considered an alcohol where I have three carbons and the OH on carbon number one, which I would call one propanol, that will be different than if I had those same three carbons, but the OH is now bonded to the second carbon, which would make it two propanol. So same atoms, same like layout, but different connectivity. The OH, instead of being connected to one, it's in this case connected to two. Instead of being connected to two, it's now connected to one. So they are known as constitutional or structural isomers. So constitutional, different constituent location. Structural is a more generic term. I'm going to be good with any of those you use. Okay, so we'll consider C5H12 and once again consider the possible structural isomers. So you need to start by considering the backbone. So it's an alkane, so you don't really have to worry about placement of a halogen or a functional group. You simply have to just worry about carbon chain length. So it could be five carbons. So that we'll always want to start with the longest, and there'll always be one example of that. So one of the five carbons, so we'll count that as one. And then you reduce the carbon chain one at a time. So for methyl groups, that means I'm going to get rid of one. And if the number of carbons gets substantially larger, then we start considering ethyl groups and possibly propyl groups. And it gets really complex really quickly. But for this simple case, we're only going to consider methyl groups. So if I remove a C to make a methyl group, then the remaining chain will be four in length. So I'm going to have one, two, three, four, and then a methyl coming off the side. One, two, three, four, methyl coming off the side. And then one, two, three, a shorter chain still with a methyl here. So then I need to get rid of identical structures. So for anybody who's paying attention, I've made the exact same mistake I made last time I did this. And I double checked with IUPAC nomenclature. So I named this. This was 1, 2, 3, 4 with Me. So this was 2 methyl butane. Not sure about that happened. And then I incorrectly named this last time, and you're hopefully going to correct me again. 3-methyl butane. But that isn't giving it the lowest possible numbers. If I were to number it correctly, which is 1, 2, 3, 4 instead, then that 3 in the beginning comes at 2. So they are the same structure, same IUPAC name. So I have 1 here, 2 here, 3 here. This one does not count. So 3 would be my answer. So systematically go through it. There's no shortcut per se. Okay, so alkene constitutional isomers. So alkenes have one unit of saturation, so it might end up being a wee bit on the trickier side, hopefully not. But we will get C4H8, the one double bond. So again, consider the carbon backbone. So could have 4 as my longest chain. But now, unlike the alkane, the double bond has to be considered. So a double bond could be between 1 and 2 or 2 and 3. So double bond here, that's 1, and then double bond in the middle, that's 2. So 1, 2. Then you got to consider the shorter chain and a methyl group, same thing as before. So one shorter than C4 would be C3. And with the methyl group, it ends up, no matter where I put the double bond, it's always going to be between the middle carbon and an N carbon, middle and N, middle and N. So there really are 3 identical structures, so just one isomer. And then last but not least, we need to consider cis and trans. So I briefly addressed this with the FATs, but just to remind you, just like with the chair conformation, same side cis, opposite side trans. So if these carbons here and here are on the same side, like they are here, this would be cis. And if those bonds are on opposite side, they would be trans. So I'm going to, instead of saying 2, I'm going to change my numbering. So this would be 2 for cis, 3 for trans, and 4. But here's the catch. As far as constitutional isomers go, these are all constitutional isomers of one another. So there are 3. These are known as stereoisomers. So this is a little bit extra of a question. So my answer, if it's worded, how many constitutional isomers? Just 3. How many total isomers? This one can be split into cis and trans. So altogether 4. Okay, just a question for down the road. That covers the, just revisit something we looked at a little bit earlier when we talked about constitutional isomers and alkenes. So kind of ties that off. And tie off one other thing we mentioned, that was units of unsaturation. So units of unsaturation, just UOU, units of unsaturation, is going to be either pi bonds or rings. Okay, so just note. And the reason it becomes useful is in a case like this. So what is the molecular formula for this compound? Well, that's kind of a pain in the butt. So if I count carbons 6, 7, 8, 9, 10, that unique ring, or unique carbons on that second ring, 1, 2, 3, 4, so 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So C28. So I know there's 28. And I remember, I think, something about CnH2n plus 2. So if that's 28, then this must be 58. That's my first thought. So it's 58. That would work out, except can't be 58 because it is not a saturated hydrocarbon. So the OH isn't going to make a difference, though, as it were. So we'll worry about that as we get into this calculation. But units of saturation do matter. If you recall, to get rid of a pi bond, it was going to take 2 H's. So we called it a deficiency of 2 H's. So altogether we have 1, 2, 3, 4 rings and a double bond here for 5 and a double bond here for 6. So we have 6 units of unsaturation times 2 H's means we have 12H deficiency. I'm going to regret that. So hopefully you can make that out to be the word deficiency, which means I need to subtract 12, which gives me 46. So that's my formula. It would be really challenging to do that, to count it out each time. But if we did, sure enough, we would get, if you trust my counting, 1 here, 2, 3, 4, 5, 6. If I go all the way around the chain, I'm going to end up eventually with 46. So the shortcut formula, very, very helpful. So where does it come from? There's got to be some sort of formula. And there is. So the formula is going to be based on the following notion. If an atom wants to keep a chain going, wants to be part of an elongated chain, so a long carbon chain, all the middle carbons have to make 2 bonds each to keep the chain going. The ends, there's always going to be 2 ends, so I'll worry about that down the road, but every carbon needs to make 2 bonds. So let's say I was dealing with oxygen. Well, sure enough, every oxygen will also have to make 2 bonds. If I had nitrogen, same thing. So basically, to keep a molecule connected, every atom needs to make two bonds. So I'm going to represent the absolute bonds needed to keep the chain going in blue, which means I have two extras. So carbon has two additional. So for every carbon, there's an extra bonding site. It can go above and beyond. So carbon, there are +2 in bonding sites. So I'm going to keep track of that. That unison saturation, every carbon has two extra bonding electrons beyond the bare minimum. Okay, I'm going to look at hydrogen. The other atom is really common in organic molecules. It only makes one bond. We need two to propagate it. So for every hydrogen, we're actually shortchanged by one. So I'm going to therefore subtract one for every hydrogen because it is only giving us one electron for bonding when you need at least two bonding electrons to keep the chain going. Oxygen, the reason we could ignore it in that alcohol earlier is it makes two bonds. It does exactly what it's supposed to do. So we just ignore it. So for oxygen, when it comes to unison saturation, we're going to ignore. Nitrogen makes 3 bonds, so it makes 2 that you need to keep going, but plus 1 extra. So every nitrogen plus 1. And then as I alluded to, there's always the 2 atoms dangling on the end. So could be a carbon, could be a nitrogen, whatever it is. They're going to be able to take on 1 extra H, if you will, or if you will, there's two dangling spots to worry about. So we have +2 for the end of the chain. So I want to emphasize that is for the end of the chain. Okay, so that's the extra bonding electrons. 2 extra for carbon, -1 for every hydrogen, +1 for every nitrogen, +2 for the end of the chain. But there are 2 electrons per bond, so we need to divide by 2. So unison saturation, that's our formula for it. So for instance, if we had a formula of C6H10O2, the calculation, the you owe it to yourself, the UOU is 2 times 6 minus 10 plus 2 for the end of the chain divided by 2. 12 minus 10 is 2, plus 2 is 4 divided by 2, 2 units saturation. If I had C28, H46O, UOU would equal 2 times 28, 56 minus 46 plus 2. So 56 minus 46 is 10 plus 2 is 12 divided by 2, 6, just like the example we just did. So you can get it from the formula pretty quickly. Okay, so let's get it structurally. How many units in saturation in this compound? Well, rings and pi bonds. So from structure, I would get it as 1, 2, 3, 4 pi bonds plus a hidden one with the carboxylic acid. Carboxylic acid groups, if you recall, are double bond O, OH. So 1, 2, 3, 4, 5, and then plus the ring for 6. So 1 for the ring, and then 5 for the pi bonds. So 6 altogether. So formula-wise, let me just see if this is going to work out. There are 6 carbons there, 7th, 8th, 9th, 10. So this is C10, H. Let's see how many H's. There are 1, 2, 3, 4, 7, 8, 9, 10. And then O's, there are 1, 2, 3, 4. So let's see how we do. I would say 2 times 10 for the carbons minus 10 for the H. Do nothing for the oxygen plus 2 for the end of the chain divided by 2. So we get 20 minus 10 is 10 plus 2 equals 12 over 2, which equals 6. It matches 1, 2, 3, 4, 5, 6. We're set. So it works for formula or structure. Looking at structure, count your pi bonds and rings. For formulas, plug into 2 times the number of carbons minus number of H's, do nothing for the O's, add 1 for nitrogen, and you're set. So for this unison saturation, we would have 1, 2, 3 for the pi bonds here, 4, 5, 6, 7, 8, and 9 for the rings. So pi bonds and rings, 1, 2, 3, 4, 5, 6, and then 7, 8, and 9. Again, I want to do the formula approach just to double check it. 6 carbons, 7, 8, 9, plus another 6, so C15. my H's would be 1, 2, 3. Nope, sorry, none there. So 1, 2, 3, 4 for the OHs. 5, 6, because there's 2 there. 7, and then 8 for an H and back. 9, 10, 11, 12, 13, 14. And then O's, there are altogether 6 of them. But I don't care about those. So 2 times 15 is 30. Minus 14 is 16. Plus 2 for the end of the chain, 18 divided by 2. Actually, let me emphasize it's 18 over 2, which equals 9. Just what we got. Formula approach or structure approach that works. Okay, so I want to try some practice. And as you can tell from the screen, practice makes you happy. These are the things you should be explaining every time you get a chance to do some homework questions. I'm so happy. Yay, hooray. I love happy time. So here we go. So which one is most likely to have a benzene ring? So first off, you need to recall what a benzene ring is. So you start by drawing benzene. Benzene is a 6-membered ring with double bonds all around it. So the quick and easy way, count your pi bonds plus rings. So 4 units of unsaturation. So now we've got to go to the formulas. You should either start with choice A, an extreme one with low amount of C and large amount of H, or choice D, large amount of C and low amount of H. I recommend starting with D because chances are you need 4, so it's going to be a lot. So let's see if that will work for me. So for this, 2 times 8 minus 11 plus 1 for nitrogen because it makes 3 bonds, 1 more than we need, plus 2 for the end of the chain divided by 2. So 16 minus 11 is 5, plus 1 is 6, plus 2 is 8. So that equals 8 over 2, which equals 4. Okay, so 4 units on saturation. So for choice D, it has 4 units on saturation. I'm going to erase everything I've drawn. So this is my whole calculation. So 4 units on saturation. It ends up, if you do this one, I'm going to just cheat and set the same thing up. 2 times 8 minus 13 plus 1 for nitrogen plus 2 for the end of the chain over 2 is 3, which makes sense. 2 more H's, so 1 less unit on saturation. This one has 1 less carbon, so that would be 2 less here. So it would be 2 and 1. Only choice D can have a benzene ring. Okay, we can use it this way. Which of these has the formula C7H12O? Quick and easy way to do it. 2 times 7 minus 12 plus 2 for the end of the chain, ignore the O. 14 minus 12 plus 2 is 4 over 2, 2 units on saturation. Okay, so choice A is possible. Could work. Choice B, not possible because it has double bond O, double bond here, and a ring, so 3. Choice C has just 1 ring, no other pi bond, so that's out. Choice D has a ring and a double bond, so that is possible. So I've actually written a question you can't answer yet. And this is foreshadowing. So this method works great to get rid of choices, but to zero in on one final choice, you need more information. So I keep on referencing IR because you did this in general chemistry, at least some of you in theory did it. And if you remember, there are certain telltale features. So this functional group is telltale. So this question would have to appear like this instead. Same question as before, but now some IR absorbance. So now we're at the same point. Only these two have 2 units in saturation. 1714 is known as a C double bond O. So knowing that means A is your best answer. So units in saturation is going to become really important for the duration of chemistry because a lot of times we'll do a reaction. We don't know what we got, so we'll purify it, we'll analyze it, and we'll come up with a formula. And from the formula, we'll have some ideas, but then we'll have to look at something like IR to get exact information about what kind of functional group it is. So hopefully this wasn't such a bad lecture. This was kind of review of everything. So 23 in the books. So with that in mind, it is time to once again say Thanks for taking part, and I will see you at the next time.